So my presentation is going to be on modified Newtonian dynamics. So these are two review articles about it. I used the first one here, and then my other source that I used mostly was Bekenstein's 2004 paper. So first I'll start with the motivation for this. So the main motivation is that in galaxies with rotation curves, at large radius you have, they flatten out. And the radius at which they flatten out is usually after you've gone past most of the matter. So there's kind of two solutions. The first is that there's a hidden mass at large radius. So this is the dark matter, and this is, in astronomy and like astrophysics, this is your conventional solution. And the other solution is you can have the gravitational forces modified at small accelerations. And so I'm going to focus on the second one here. And then in almost all galaxies that we observe and we make measurements of, you need more dynamical mass than you observe. So this is kind of a generic feature, and it's not just in rotation curves. So this is just a plot of some different rotation curves for kind of 8 different galaxies. And so in most of these galaxies, like kind of this region here, that's when your stellar content starts to stop, and that you're more in the kind of the dark matter or MOND regime. So this is just an example of the rotation curves. And this was taken from that review I mentioned. Okay, so first I'll start by defining kind of MOND as it was first envisioned, and this is why Milgrom in 1983. And so what we want to do is we want to modify Newton's law at small accelerations. So instead of saying ma is equal to minus the gradient of the potential, we want to say it's some functional form of the acceleration times the acceleration, and that gives us our potential. And so this functional form is basically for large values of x. You just have your normal gravitational force here. But for very small values of x, you have the acceleration goes as the square root of the gravitational force. And so this constant was estimated as kind of 1 times 10 to the minus 10 meters per second squared. And so this is a very tiny value. And so this is something that I think I have a figure in the next slide that shows kind of where you get in this regime. But it's, this is something we're never going to see in the solar system. And, we'd have to make, maybe need 200 years in experiments to, think about measuring this. And so this equation down here is our modified Poisson equation, where you just have this functional form in here. And so one thing with MOND is that how it's defined is you just have these kind of functional limits that you need to meet, and this function is kind of some unknown thing that we have to figure out, and we're going to figure out by looking at a more specific theory. Okay, so this is just a figure of an acceleration scale. So the sun's somewhere over here, and these are all the different figures or symbols for the planets, and these are kind of satellites we put out there. And these are the acceleration scales that are felt like galaxies. And so this is kind of the regime where you start to see modified gravity. So this just kind of shows, where we would see this regime. So I kind of said what the MOND kind of formula is, and so here's just a kind of brief derivation of how it gets your flat rotation curves. So if we look at the MOND limit, so normally our Newtonian potential is just Gm, or the gradient of the Newtonian potential is just Gm over r squared, and so we want to set that equal to our centripetal acceleration. And so this part here, let's see. So if we use the MOND formula, you get a squared is equal to a squared over a naught is equal to minus the gradient of the potential. And then if you just set the acceleration equal to v squared over r, you come up with this formula here, which is v squared is equal to a constant. And so this is kind of where the motivation for the functional form of mu comes about, where we just want to get this v squared is equal to a constant. And so this is kind of just at your MOND limit at large radii. And then just kind of as an aside, one kind of an astrophysical measurement or correlation that's been noted is called the Tully-Fisher relation. And it basically says if you measure the baryonic mass of the stars and the gas content, and then compare that to velocity, it goes as the fourth power. And as far as I know, in normal land of CDM, that's kind of still up to debate why that's caused. And one thing that MOND kind of predicted this, even before that measurement had been kind of set in stone and measured very precisely.
So that velocity is an average velocity?
I think it's usually your velocity at large radii. Yeah, I think that's usually how it's defined. Okay. So now some issues with kind of the formalism as it was written before. If we just take that MOD formula and add it on to our Newtonian mechanics, first of all, it doesn't conserve momentum. So this is bad. Second, the theory isn't relativistic, and so we want to make a more kind of general relativistic formulation of it. There are some inconsistencies in the theory. This is the explanation that was in the paper is if you take a star that's kind of very far away from the center of the galaxy, it will have a very small acceleration. So the star in the center of mass of the galaxy's frame. But if you look at the gas particles within that star, it will have Newtonian mechanics kind of affecting it within the star. So it's kind of, there's some inconsistencies there. And then it says nothing about cosmology or gravitational lensing, which is effects that have been measured very precisely now. And so we want to make kind of a consistent relativistic theory that can address these views here. Okay. So first I'm going to talk about kind of the three starting points for the theory, and then I'll talk about kind of a successful one. So this was something that came out almost immediately after the MOND theory was written down. And this couples a scalar to the physical metric. So you have your metric is g tilde here, and it's equal to e to the 2 phi. So phi is some scalar times g alpha beta. And so g here is your normal Einstein metric. So that'd be your Frederick-Robertson-Walker metric, or your source-follower metric, or whatever you want. So this was, if you remember back to the first talk, this is the same conformal thing that we looked at in the two-dimensional gravity. So we couple a scalar to the physical metric. It has a Lagrangian density that has this form. So f is some unknown function, but it's made out of invariance here. And then you'd write down your action with your Ricci scalar, and you'd add that in, and then you'd vary your action and whatnot to find your Einstein equations. I didn't write that down, but that's done in detail, I think, in this paper. And the upshot is that you can get the correct MOND dynamics in the correct limits. So you can get GR, you can get MOND here.
Sorry, what is capital L? I missed that.
L is some length scale. So it's
which is of the size of a galaxy or something like that. It must be pretty large scale.
I think so. I don't know what it is in this theory, but I'm guessing when you go to the MOND dynamic scale, it will be related to A0.
Right.
But I don't remember what it was for.
It's some function.
Yeah, and I guess I didn't mention, but this is called a quadratic Lagrangian theory, so A-qual.
Well, to be quadratic, then f tilde has to be linear, right? In fields, it has to be a quadratic function. So
yeah,
I'm just trying to understand what f tilde is.
I don't think it was specified. It's just kind of, it has some known form that is done in more detail other places. Okay. So this can get your MOND dynamics, but it doesn't get you gravitational lensing. So I guess gravitational lensing just, I think someone's giving a presentation on that. But I think you get an extra factor of 2 opposed to Newton's theory, and also you will need dark matter or some extra matter. And so this theory as written down doesn't solve that. The next problem is that your scalar waves here, So this should say acausal, but they have acausal propagation, so they will usually propagate faster than the speed of light, and that's a big problem. And so, this theory as it's written down is kind of ruled out because of that. And this last thing is your kind of final equation of motion here. This phi is your scalar field, and depending on the value of phi there, you'll get MOND dynamics or Newtonian dynamics, whether it's kind of small or large. Okay. So let's move on to the next kind of idea for MOND. So this one's called phase-coupled gravity theory. This is an extension of the previous one, where you still assume that your metric has the conformal transformation, but now you have two coupled scalar fields. So phi here is the same as it was before, but A is your kind of second scalar field. Oh, that doesn't sound right. But your phi is coupled to the matter and it's coupled to the metric, whereas this A here is just coupled to your phi scalar, and it becomes non-dynamical. This eta here is some small parameter, and because of that, this term dominates over this one in the theories. Or this term is usually negligible, so it's ignored. And the main motivation for this is it fixes the causality in the previous theory that I wrote down. And so this last thing is you can go through your Einstein's equations and whatnot and go to your MOND dynamic limit with your small acceleration. And so you can get your MOND dynamics in galaxies. But in this theory, those same kind of parameters, so that would be your eta here, would explain galaxies, but would be kind of too large for the solar system. It would also kind of fail for gravitational lensing. Okay. So the next kind of idea here, this is kind of a group of theories. This one is a disformally related metric. So this last term is your disformal term. And so this term is kind of tacked on, and then this will give you gravitational lensing via this last term here. The only problem with this is that when you work it out, is that in order to have deflected light increased, like we need for gravitational lensing, it'll actually decrease it if you want causal propagation. So this is kind of ruled out also. There's an okay, I won't mention that. Okay, so now these are kind of three different ideas that all don't work.
So here you're back to a single scalar, though, aren't you?
Yes.
Right, you have the psi field, and then you just have a little bit more of a complex structure as far as the coupling is concerned.
Yeah.
Right? You don't have the A field anymore, in other words, that
you
had in the previous one. Right?
Yeah. I think there are multiple theories to write down this way. So that kind of segues into this. So the solution is called TVES, so this stands for tensor vector scalar. And so it's effectively combining the last three ideas together. And so this is Bekenstein's 2004 paper, and this is kind of the first, MOND theory that correctly worked for gravitational lensing. And so the tensor it refers to as your Einstein metric. This vector is your mu alpha here. That takes the place of the phi derivatives in the metric here. And then you have your same scalar before. And then you also, what was written as the A scalar before is written as sigma now, so it's a non-dynamical scalar. So now our physical metric looks like this. And then, so now we want to write down an action and solve the Einstein's equations. Okay, so I copied the actions here from the paper. We won't look at them in detail. The most important thing here is you have three independent parameters here. It's supposed to be little k, L, and k. So L here I believe is a length scale again. And then these two k's are both parameters. There's also a free function f, which is in this term here. And this will be related to your MOND function. But other than that, this is your action. And now to get anything out of this, we have to do the variational principle. So I will cheat and just copy down what was written in the paper. And this isn't actually the complete equation because tau here and capital sigma are big, long equations. I didn't want to go through all the time writing all this stuff down. But the most important part is, so this is G alpha beta here is your Ricci tensor plus the Ricci scalar. And so what we want to do is we want to look at this equation in the GR limit. So in the MOND theory, our GR limit is we want little k becomes very small, L is proportional to k to the minus 2/3, and this capital K is proportional to little k. And what happens is that you get back basically Einstein's equation plus some small correction here. And this correction here, I think they assumed it was a Frederick-Robertson-Walker metric. If you do like a Schwarzschild metric, you'll get like an order correction that's proportional to big K there.
The F function that you had, or was it called the G function on the previous transparency? Right? The F function.
This one here?
That's basically known because you know the mu function from the galactic rotation curve fits, right? You showed a plot of that before, right?
So,
is that the case? Or?
So I guess how it says, so you would find what it is by fitting it to something.
Right.
But like when you just write down the theory here, you don't know kind of what it is.
Of course.
So it is.
But you have an idea, right?
Yeah.
It has to have that shape.
Yeah. So as it has to have the you want a MOND limit. You want it to go to 1 in the MOND, the Newtonian limit, and you want it to go to x in the MOND limit. So as long as it takes that form, it can be whatever you want.
Right. But here there is a relationship, you say, between the F and the mu, right?
Yeah. I don't.
You can work it out, presumably. Right?
Yeah.
And then the mu is known from fits.
Yeah. Yeah, in the Bekenstein paper, there's a form that he uses and says, this produces all the results, but I didn't write it down here.
Right, so it's,
Okay. The last thing is you have a non-relativistic limit that gives you your Newtonian mechanics and then your MOND mechanics. So I think somewhere psi turned into phi. But this should be our scalar field. And then you can work out what A naught should be in terms of your various constants. And this phi sub c here is going to be kind of your background density, what the background density of your equation should be based off cosmology. Okay. I think the last thing I'll talk about is gravitational lensing. So how this fixes gravitational lensing. He writes down a metric here for the Einstein metric. And so this nu and this s here are going to be related to whatever your matter is in your universe. And then this is just your normal kind of spherical symmetry. So here, this is your lensing deflection angle, so how much an angle will be bent. And so here, nu and s will be dependent on whatever the matter is. So if you're in cold dark matter, these will be determined by both dark matter and visible matter. Whereas in MOND, you'll have only these terms dependent on visible matter, and then you'll have this extra phi term that will be able to increase your lensing. And so this is kind of a proof of principle that you can get lensing. Okay, and this is the last thing I have. This is basically a table that shows what MOND can and cannot get. And where it has problems. And mostly it's kind of the top stuff is all gravitational dynamics, and it works pretty well. And this bottom stuff is cosmology, which it doesn't work as well for. And then you can see there's a whole bunch of stuff that I didn't really mention or have time for. Okay, so thank you. Do you guys have any questions? So the Tully Fisher, like it like just straight out comes from that relation. I think that's one of the main things why people like it. It's still like a kind of hands up in the air for why lambda CDM would get that. I think also the Faber-Jackson relation gives that too, where that's like m is proportional to sigma to some power. But these are, astronomy correlations that we're not sure why they exist, that this kind of predicts it. But this kind of theory in general just has more cosmology problems than dark matter does, whereas the normal lambda CDM model has problems with kind of small scale structure.
Can you say maybe a few words about what those problems are in cosmology? I mean, what does it come down with? What are the most significant deviations from lambda CDM?
So they're all in areas where you have baryonic process happening. So so I study some of this. So one of them is you have like the missing satellites problems. So you say cold dark matter simulations predict thousands of satellites around the Milky Way, and we observe less than 30. You have the core cusp problem, where it says that so with a simulation you should have an R to the 1 type profile at the center of galaxies. This is CP rising. And then in nowadays most galaxies you observe something that becomes a chord, roughly flat. So these are kind of effects that start to come about in the center of galaxies. And a lot of people think these are just solved by including the correct baryonic physics. And there's others that I haven't mentioned. But those are two that I know.
Does it include dark matter, or not dark matter, but dark energy or a cosmological constant?
Well, I assume everything I talked about, you could just add a cosmological constant to this, and then you're fine. Do you have a question?
I was going to say, I remember you said this, but can you combine MOND and dark matter?
Probably. You could probably do that. And I think in this review article that was mentioned somewhere. So you could probably do that, and maybe that could fix some of these problems.
I mean, MOND looks like an increasingly contrived form of a scalar tensor theory, right? Where you have more and more complicated scalar interactions, and maybe more than one scalar. And of course, those are similar to the Brand-Stickey theory that we discussed in class. And so you can tag on anything you want. You can have a cosmological constant term. You can have some other terms in the sense that it does still respect general covariance. Right?
Yeah.
So the interaction is still formulated in an invariant way. It's just that you have more fields. You have basically a new fundamental force, right? Because you have this extra field that is massless, so it gives long-range interactions.
At least from astronomers, most astronomers do not like MOND at all. They're very in the cold dark matter paradigm. But I think part of the reason why it didn't come about, or it isn't accepted, is that it basically took 20 years for a kind of reasonable covariant theory to be written down. So it took a while for that to happen. I was going to say something else, but are there any other questions?
So those problems, do they exclude MOND, or do they just say that we need more stuff?
They're probably more on the problematic ones. Yeah, they're probably more on that. So I guess some of it is you could write down a different Lagrangian type theory, and then maybe that could fix some of these. Or I don't know if these are generic, MOND predictions that these just don't work. But you can see that as kind of time went on, more and more of these problems got fixed. So the other thing is, with MOND, you have 1% of the people working on this compared to dark matter. So there's a lot of stuff to be done. I guess the quote I'll use by some unnamed physicist here is, "I find MOND very fascinating, but I would never let a student work on it." So, any other questions? Okay.
Thanks.
All right, hi, I'm Craig. I'm going to be talking about dark matter. So first, how the idea of dark matter came about. It was first proposed by Jan Oort, who's the same astronomer that named the Oort cloud and is famous for a lot of other things. and this was way back in 1932. He saw that the orbital velocity of stars around the Milky Way seemed to be too high given the luminous content, so as in the gravity due to stars and gas and dust. And it was also proposed in 1933 by a Caltech astrophysicist who found that the velocity of galaxies in the Coma cluster were about 400 times greater, although his calculation had some problems with it, but it's still a lot greater than the expected value just based on luminous matter. And then he actually coined the term dark matter. So to understand some of the problems or why we need dark matter, we should look at the rotation curves. So if we look at the rotation curve for our solar system on the left, then we see it fits a nice 1/r trend. And on the right, there's a rotation curve for the Milky Way galaxy. But the red line is a prediction just based on the luminous matter distribution. And we see that there's actually a flat rotation curve. It doesn't fall off as the distance increases. And so presumably that extra gap would be filled in due to the dark matter. And so in the 1970s, Vera Rubin showed that actually most or all spiral galaxies exhibit this flat rotation curve, and there's a couple examples there. And we measure the speed of the stars. Well, actually, they measure the speed of the gas in the spiral galaxies by looking at the red and the blue shift from the 21 centimeter emission line. So this gives rise to the idea of dark matter halos. That is, there's a halo of dark matter that becomes more and more prevalent as we pass, say, the 10 kiloparsec distance in our galaxy. And approximately 90% of the galactic mass is calculated to be dark matter. And this was calculated by Vera Rubin again. And right, this extra mass is what keeps the rotation speed constant as the distance increases. So this brings up the question, what is dark matter? There's a lot of evidence suggesting that there's something else out there, but we don't know what it is yet. It's about 23% of the energy content in the universe, and dark energy is about 73%. And then the stuff we know about is roughly 4%. And studying dark matter combines general relativity, since we basically measure dark matter, at least so far, only by gravity. Although we can measure it by the weak force, perhaps with Wimps, which I'll talk about later. And we need cosmology as well to understand the origin of dark matter, how dark matter would change the evolution of the galactic structures, and then particle physics for the dark matter candidates. First, we'll consider the neutrino as a dark matter candidate. So we know that neutrinos are everywhere, and there are billions of neutrinos passing through our bodies every second. And they're hard to detect and don't interact electromagnetically, so they're dark. Originally, the standard model predicted neutrinos were massless, but it was theoretically proposed in the 50s that they had mass, and then this was experimentally proven by Super K in 1998 from neutrino oscillation measurements. And neutrino oscillations, they actually tell us delta m squared. They don't tell us the actual mass eigenstate values. So from various experiments, delta m21 and delta m13 and so on have been measured. The distance from 0 is not known yet, so we don't actually know what exactly the mass eigenstates are. But the sum of the three mass eigenstates is less than 0.3 GeV, or 0.3 eV rather. So they're extremely lightweight, and this is a candidate for the hot matter model of dark matter. So hot matter means that it's moving at relativistic velocities. They're so lightweight that the gravity that would attract them to each other is going to be easily overcome by their velocities, and so they wouldn't really clump together. And this doesn't really seem to be consistent with the dark matter distribution that we see. But there could also be sterile neutrinos, which they don't interact through the weak force. And these are predicted to have a long lifetime, but they decay into X-rays, which could be observed. So searching for sterile neutrinos has been done by Miniboon, and Miniboon ruled out sterile neutrino mass of less than 1 eV, so they would have to be much more massive than ordinary neutrinos. And then the integral satellite ruled out the mass range between 40 keV and 1 MeV. And there have been other experiments, but there's still a lot of parameter space that hasn't been explored yet. There was recently a paper published by Professor here, and it's titled Resonantly Produce 7 kiloelectron-volt sterile neutrino dark matter models. And you should read that or look at that paper if you're interested. I'm not really going to go into details about it. But basically, in his paper, he explains the unidentified X-ray line from galaxy clusters, and the X-ray source being the decay of the sterile neutrinos. And he also, in the paper, attempts to solve the problem regarding galactic formations. So neutrinos, their sterile neutrinos may or not be the dark matter particle. There are a lot of other candidates, such as Machos, and that stands for Massive Astronomical Compact Halo Objects. And Machos are just made of ordinary matter. So there are things like neutron stars, black holes, brown dwarfs, red dwarfs, which are very faint stars, wandering planets and asteroids, and maybe starships. There's a lot of other things in the universe besides just gas and stars. And these don't directly emit light, but we can detect them through things like gravitational lensing. And I'm not going to go into that very much since Anna's talking about that next. But we know that massive objects will curve space. And this curved space acts like a lens for the light. And so if we look at the picture here, the middle picture is when a macho object has passed in front of a star. And so the light sort of spreads out around it, becomes much more spread out. And so I think this is called microlensing. And these events are fairly rare to detect, but nonetheless we know that it's a real phenomenon. So, and then we can measure the angle of deflection. I guess this picture sort of shows the difference between the apparent position and the actual position by the bending of light. So while it's difficult to add up all the Machos in the galaxy, we know that it would have to be 6 to 10 times as much stuff compared to luminous matter. So that just seems pretty unlikely that ordinary matter would be a candidate for dark matter. And due to various experiments and Hubble telescope observations, it's estimated that Machos make up about 3% of the Milky Way's mass. So perhaps would account for some of the missing mass and dark matter, but that's not the final answer. So then there are things called Wimps, which are weakly interactive massive particles. And these were named deliberately in contrast to Machos. So instead of big macho objects, we have little wimpy particles. And they're predicted to have been produced just after the Big Bang. So they only interact with a force similar to the weak force in scale. And so this is an example of the cold dark matter models. So these are high mass particles, and so they would be much slower and they would attract each other much more. And so it seems like a much more plausible model than the hot dark matter. So perhaps one possibility is that a WIMP is a supersymmetric particle. And so in order to have the predicted self-annihilation cross-section, basically the dark matter and anti-dark matter WIMPs annihilating of 3 × 10⁻²6, we have to have a WIMP around 100 GeV. And so this is a particle that could be predicted by supersymmetry. Although, I guess I have these slightly out of order. Although, basically, an experiment called LUX and super CDMS haven't seen evidence of supersymmetric particles, nor has the Large Hadron Collider. So while supersymmetry is still a thing, I guess it seems unlikely to be, I guess, true. So I guess I don't want to say that because I might get some verbal abuse by people in the audience. But there are other WIMP candidates. So there are 2 different types of ways to detect WIMPs, directly or indirectly. So from direct detection, we're basically looking for the collision of WIMPs with ordinary matter in the lab, like nuclear scattering. So in order to minimize background, the detectors are buried very deep underground. So in this picture, we have the Sudan mine in Minnesota. And I don't know if you can tell, I think it says 2,341 feet underground. And I think this is a CDMS experiment. And so we know that we would see an annual change in the signal, basically from the Earth's movement about the dark matter halo by going around the sun. But these detectors would have to be extremely sensitive. So a couple of direct detection experiments have been CDMS in Minnesota. And for this experiment, they have cold germanium and silicon crystals, and they're cooled to 50 millikelvin. So a WIMP passing through would collide with a atom inside of the crystal. And this collision would cause a vibration that would heat a layer of superconducting metal. And so you can actually just measure the change in resistance that's due to the change in heat. And so they're trying to look for those small changes in resistance from a collision event. It was announced in December of 2009 that there were 2 events that could have been caused by WIMP collisions. So definitely not statistically significant data to claim anything yet. And then there's another experiment called Cogent, and it just has a single germanium crystal. And they reported hundreds of events, but a lot of people are skeptical that these aren't actually caused by something besides the WIMP collisions. Perhaps by like a radioactive decay process from a nearby source or something. But from this experiment, their events suggest that the WIMP would be between 7 and 11 GeV.
2 events over 1 year or 5 years? Or?
I think it's
Probably 1 year only, right?
Yeah, it's not over. It's a fairly recent experiment. It's not over that long of a time, but there's a more.
I think 1 year too.
It's probably 1 year. It's the first year of operation.
It was the first year they didn't get anything, the second year they got 2 events. I think the first year they didn't have anything, the second year they had 2 events. So I think it's over a year, but it was running for 2 years.
Oh, okay. So besides the direct detection experiments, there are a lot of indirect detection experiments for WIMPs. And we're looking for basically decay products of WIMPs. So typically we look for excess gamma rays. So gamma rays would be produced from the final state product of annihilations of WIMPs, and they could also be produced as charged particles. I don't think I worded that correctly. well, okay, I'll just skip that. In this picture, we have the Fermi telescope, which has been operating for a couple years, several years. And so the Fermi telescope is looking for excess gamma rays from the center of the galaxy. And back in 2010, NASA said that only 30% of gamma rays are actually from the active galactic nuclei. So that leaves a large portion of the signal to have an unknown source. And the Fermi telescope hasn't actually confirmed an annihilation signal, but has put some bounds on it. So there are a couple other experiments, such as IceCube at the South Pole, and they're looking for neutrinos that were generated from WIMP interactions, although there hasn't been enough events that have been detected yet in order to say anything conclusive about whether the neutrinos were from WIMP interactions or not. And then in this picture is the Veritas experiment, and that's in Arizona, and it's an array of 4 gamma ray telescopes. And so, all these experiments have just been probing different, areas of parameter space. There haven't been any signals yet, but I guess a null result isn't. It's still progress in some ways. So we just heard about MOND, so I'll skip through this. This is sort of a, if you're losing the game, change the rules approach. And it's not very popular among astronomers, although it does fit the data for the rotation curves pretty nicely. But it doesn't really have an underlying physical theory. It just fits the data, so I guess it won't be taken as seriously until it can have some kind of underlying physical explanation to go with it. So what's in store for dark matter searches? Well, there are a lot of experiments that will continue looking for Wimps, which seem to be the favored candidate for dark matter. You can also look for axions or other particles that people might come up with in the future. And there's my image credits. I guess my references were just sort of too many different random websites to count. But that is my presentation. Any questions?
Do they know if the dark matter is uniformly distributed, or is it clumped, or when you look at just the Milky Way?
I guess.
Or if they look at gravitational lensing as basically the best way of determining it, is it clumpy or is it uniform?
Yeah,
around a galaxy?
I think it's a uniform halo.
Okay.
Yeah, but I think as far as lensing goes, it's easier to tell from looking at the lensing from galaxy clusters, more so than just within one galaxy. But I think
No. Big clumps.
This picture is right.
Yeah. I guess in models I've seen, it's uniform. Yeah. Okay.
Questions?
Okay, so when I go full screen, it chops off part of the screen. So I'm just gonna leave it like this instead of going into presentation mode. Okay, so thanks for sticking around. So as you heard, I'll be talking about the hierarchy problem and the Planck mass. Oh my goodness, this is gonna be fun. Okay, so the hierarchy problem starts from a very natural question, right? You can look at the coupling that controls the weak force, which is the Fermi constant, and you can compare that to the Newton constant, which is the analogous coupling constant that you see in gravity. And you see that there are more than 30 orders of magnitude apart. And of course, this seems very odd. Any physics student would look at this and immediately think, why is this happening? Of course, there might not be any reason. There's no reason that all the couplings have to be 10 to the minus 5. So maybe there's nothing behind it. But let's see if we can rephrase this. So instead of talking about a coupling, let's talk about masses. So for each of these cases, I can rewrite these couplings in terms of characteristic masses for the weak force and for the gravitational force. So for the weak force, I can talk about the Higgs mass. And for gravity, I get the Planck mass. And of course here, I see that there's a big discrepancy. So I can change my question a little bit, and I can ask, OK, so why is the Higgs so light? Why is it not as heavy as the Planck mass? And again, this might not even matter. There might not be a good reason why these two things should be similar.
Well, the Planck mass is not a mass of anything.
That's right, yeah. Most definitely. So there might not even be a good reason for them to be similar. But let's take this a little bit further. So let's now look at just the Higgs mass. Let's ignore everything about gravity. We know that the Higgs mass is a quantum particle, so its mass is going to have quantum corrections. You can do a loop calculation like the one I have here, which is a top loop. And you'll find that the first contribution you get diverges quadratically. And that's really bad because you can't renormalize it. And you're just kind of stuck. So lambda, in this case, should be as large as possible. So you expect lambda to be as big as whatever the next new physics is. So above the weak scale, the only other physics we know about, the only mass that we know about is the Planck mass. So you would expect that with this quantum correction, the Higgs mass should be gigantic. It should be comparable to the Planck mass. OK, so we can look at a couple of solutions. The first one is instead of actually solving the problem, we'll just, instead of actually answering the question, we'll just remove the problem altogether. So in supersymmetry, we can get new diagrams like this due to new particles. And they will also contribute to the Higgs mass. In this case, they end up canceling out the quadratic divergence. So we haven't answered why the Higgs mass isn't really heavy. We haven't answered why the two forces are very similar, or aren't very similar. But we have removed any good reasoning why you might expect the Higgs mass to be very large. However, we haven't found supersymmetry yet, and it might not be there. So maybe we should look for something else. Another very common solution is to look at extra dimensions. So typically how this works is you have multiple extra dimensions, and it makes the gravitational force weak because the gravitational field can leak into that extra dimension. So if we're only looking at 4 dimensions and it's leaking into 8, then we're going to see a gravitational force that is much weaker than what we would be expecting. However, these models are pretty tightly constrained. So if I only have 1 or 2 extra dimensions, then it's going to be very difficult to get a gravitational force that is very weak as we see it. So there's one other thing we can do in the mindset of this second case. So instead of looking at just an extra dimension that is flat, we can look at it at an extra dimension which is curved or warped. This is also called the Randall-Sundrum model. So how this works is you only need 1 extra dimension, which is kind of nice. Here we're going to call it z. And it doesn't extend out to infinity. It is truncated between 2 branes, one that I call z equals r and r prime, or uv and ir. And how you should picture this is that each brane is a 4-dimensional brane. So the 4 dimensions that we see are located at r prime, so at the ir brane. So all the particles we know about, electrons, protons, and whatnot, are all fixed at r prime. Gravity, however, can travel in the bulk, which means it sees all 5 dimensions. It can travel in the z direction, the way I've drawn here. So there's the naming UV and IR. You should associate R with the Planck mass, and we'll see why that is a little bit later. And you should associate R prime with a TeV scale, so something around the weak scale. Cool. So there's one interesting thing about Randall-Sundrum. If you write the metric in this way, your metric is conformally flat, which means that at every value of z, it looks just like your normal Minkowski metric, right, with just some overall constant sitting out in front. So let's talk about this intuitively first. So you can kind of already see how this might solve the hierarchy problem. First off, because of the way this metric is formed, as I go closer to the IR brane, right, my metric, or in other words, my ruler that I'm using to measure things, is getting smaller. So everything is starting to look bigger and bigger. So distance and time expand, but correspondingly, energy and mass shrink. Right? So mass being what gravity sees, mass and energy being what gravity sees. So already you can kind of see that gravity is very weak near the IR brane. Another picture is a little less clear, but I think it's worth mentioning. Because this extra dimension is warped, gravity looks a little funny in that direction. So if you were to look at the quanta of gravity, the gravitons, you see that their wave functions in the z direction are pushed very closely to the UV brane. So its overlap with the IR brane is very small, so you can see that it already is not affecting things at the IR brane very strongly. So it has very little overlap with particles that we're made out of. So already you can kind of expect that gravity must be quite weak. Okay, so let's actually do a little bit of math and see how this goes about trying to solve the hierarchy problem. So we can look at the Einstein-Hilbert action, both in 5 and 4D. So 4D is the one that should look familiar. I've written it in terms of the Planck mass instead of Newton's constant. On the left-hand side, we have the 5-dimensional one. You notice I have one extra factor of the Planck mass, and that's just for dimensional reasons. And I also differentiate between the Planck mass in each case. In principle, they might be different. So whenever you're working with extra dimensions, you can write down an action. You want it to have as many integrals as there are dimensions. If you want to know what the universe looks like in 4D, you can just integrate out that extra dimension. So in our case, if we want to know what things look like on the IR brane, we can just integrate out the z dimension. And so that's what I do here. So I explicitly write it in terms of r and z. So I'm just pulling things out of the metric here, so it's a little bit more explicit. And I'm left over with this factor sitting out in front. So notice, as I said before, r corresponds to something that is order the Planck mass, right? So dimensionally, you can see that r must be 1 over the Planck mass, order of magnitude. R prime is 1 over TeV. So this whole factor here is very small. So I see that this whole constant sitting out in front depends, or doesn't depend very much on r prime. So it really only depends on r here. Right, so if I compare the 4D action with this action here where I've integrated out the extra dimension, I can pick out what the Planck mass is, right? I can just drop this term, and I can just compare the two. And I see that if r is about the Planck mass, that the Planck mass in 5 and 4D is very similar. They're about the same order of magnitude. And also, it's interesting to note that it doesn't matter how I choose r. since both Planck masses are very similar. R can be associated with either one. Okay, so that's half of the problem. The other part of the solution is going to come from actually looking at the Higgs. So we know that just looking at gravity alone is not enough to see that the problem is solved. We need to see what happens at the IR brane for Higgs and other particles. So as I said before, all the standard model particles are fixed to the IR brane. So talking about them in 5 dimensions is kind of moot, right? The integral that I would be integrating over is trivial. It's just a delta function. So I'm just going to write it in terms of 4 dimensions. I can expand out my metrics, and I see that I'm just evaluating z at r prime because that's where the IR brane is. Okay, so this looks a little messy. One thing that's kind of annoying is that my kinetic term is not canonically normalized. So I'll redefine my Higgs field such that it is canonically normalized. So I'll just multiply it by r prime over r, and I get this action at the bottom here. And I see that all the factors of r over r prime have disappeared, except for the one that corresponds to the Higgs mass, right? So mu here isn't the Higgs mass. This is, though, closely related to the Higgs mass. So what I see happening here is r over r prime is a very small number. What this warping is doing is it's warping down the mass of the Higgs, right? So the mass of the Higgs could be a very gigantic number, but this r over r prime is going to warp it down to some very small number. So if r actually does correspond to the Planck mass and r prime corresponds to TV, I can warp it all the way down to the weak scale, and I can actually get a Higgs mass that makes sense and is consistent, despite all these gigantic quantum corrections. Okay, so that's a big conclusion here, is that RS with very few assumptions can solve the hierarchy problem. But not quite, actually. Right? We've just replaced the hierarchy problem with what's commonly called the radius stabilization problem. So why is R so much smaller than R prime? Right? There's no explanation so far in how we've presented this that is the case. Right? I've fixed R and R prime such that it actually solves the hierarchy problem. It turns out that there's a way out of this, and it's introducing a field called a radion, but that's a bit outside the scope of what I want to talk about today. So, do you have any questions?
Questions? So the extra dimension has anything to do with the Kaiser-Klein theory?
Say that again?
Karu's,
Oh yeah, most definitely, yeah. So Kaluza-Klein typically assumes that the metric is not warped, but it will end up working the same way. So in Kaluza-Klein, typically you'll integrate out that extra dimension just like we did here, and you'll get Kaluza-Klein modes. And that's exactly the same thing that happens here too. So that curved line I drew of the graviton peaking up towards the UV brane, that is the lowest Kaluza-Klein mode for the graviton. So it's very similar, yeah.
Somebody's going to give a presentation on Kaluza-Klein, I think, at some point.
Yeah, I was trying to avoid talking too much about Kaluza-Klein, even though having that beforehand is very helpful for understanding RS. But
the other thing is that when you write down the scalar curvature in 5 dimensions, it's different, of course, from the scalar curvature in 4 dimensions. There's all the extra components. These are the fifth part of the metric.
Maybe answer my question. Anthony, when you were integrating the 5th dimension out of the Einstein overaction, can you go back to that slide?
sure, I did something a little bit cheeky, yeah.
Oh, you did?
I did, partly because a lot of reviews, I'm not sure if they do it correctly,
Yeah.
so I tried my best to do something that made sense, and the result is still the same, even if I have a power mistake. So the Ricci scalar that's in the top line here,
Yes.
That's the 5-dimensional one. Right, that one is in principle not 0 because there is, like, space is actually curved here. There's some warping. If I were to just try to write down what the Ricci scalar is for some value of z, it's just 0 because it's flat space. But implicitly, what I'm actually doing here is I'm expanding about some small perturbation in my field, and that's what is keeping this non-zero. So yeah, at this point, I'm actually also looking at integrating out the extra dimension, and there are some zero-mode gravitons flying around, and that's what's making up R, I believe. That is my interpretation, but I've not done too much with that.
And so the R in the second line down is the same as the 4D R?
It should correspond to the same thing there, yeah. Yeah.
Any other questions?
How constrained is this model?
OK, good. So the model that I've presented here is actually very tightly constrained. There's a lot of phenomenological problems with it by itself. And that's more on the gravity side than on the fact that there's standard model particles involved. I don't know exactly how constrained it is, but I know that no one really studies it anymore with having all of the standard model on just one brane. So what a lot of people do is they have the standard model particles in the bulk, and there are just so many different ways that you can set it up that it's very easy to, not very easy, I mean all of the models are very hard to do, but avoiding bounds becomes much easier. Yeah. You can also do like a lot of really interesting things with having the standard model in the bulk.
Okay, very good. Thank you.
Sure.
All right, hey everyone, my name is Mo. Sorry for sticking around. Yes, it's inflating, don't worry. So I'll try to make this feel as quick as possible. So I decided to talk about inflation because this has been a hot topic this year, although as I'll explain at the end, this might be for the wrong reasons. So in the beginning of the universe, it was a hot plasma, so it was ionized, and the photons were trapped. But as the universe cooled down, the plasma condensed into neutral atoms. All of a sudden, it's invisible, and the photons can escape. So they'll travel for 14 billion years. They'll curve around the galaxies. They get scattered. They get redshifted. And meanwhile, we humans evolved and spend $1 billion on a space telescope, which at some point sculpt the photon. And then we take all those photons and try to analyze them. And with a lot of work, you can reconstruct this. Basically, the last signal we can see from the early universe. So what you see here is a temperature map. It's a temperature of the photons we see from the early universe. It's called the cosmic microwave background. And the reason why I see different temperatures, it tells you that you had regions of over-densities or under-densities in your plasma, which meant that the photon had to climb different gravitational potentials. So some of them got redshifted, some of them got blue-shifted. And this is not just a useless a plot of noise, because these densities were the seeds that formed large-scale structure later in the universe. So it's pretty much worthwhile to ask, why is it so non-uniform? How did those form? However, an equally important question is, why is it so uniform? It's because if you look at different patches of the sky, just in a standard cosmology, then the longer you wait, you'll see bigger, your horizon, what you can see, grows up. Like next hour, my universe is now bigger by a light hour. I can see more. So if I rewind it back in time, I should see less. So if you take different patches, just separated patches of this map, and rewind them back in time, they don't see each other. So why are they in thermal equilibrium? And they are. The difference in temperature here is 10 to the minus 5. And if you fit it to a black-body spectrum, the fit is so great that you can't see the error bars. And yes, there are error bars here. You can't see them. They're so small. So this is called the horizon problem, which inflation tries to address. So to put it in context, let's to use a little bit of math. So we take, as usual, in our universe, take the FRW metric. There are two important quantities we define. One is the co-moving Hubble radius, which tells you what things are within your causal contact. If you integrate this quantity over some time, then you get what's called the co-moving horizon, which is what things wherever in your causal contact, if you're farther away from me than my co-moving horizon, then there is no way I could have ever been in causal contact with you. And this is a problem with the CMB, is that each 1 degree angle of the CMB is farther away from the rest of the sky by more than the co-moving horizon. So if you want to fix this, you want to increase the co-moving horizon. You're going to make it bigger. And since the co-moving radius, as we said, is going to shrink as you go back in time, one way to remedy this is to increase the contribution to this integral by making this quantity large in the early universe. And this is what inflation tries to achieve. So we can see it more visually here in this plot. So this is a plot of the history of the universe and the surrounding cosmology before inflation. So the vertical lines are spatial slices, the horizontal lines are time slices. So we're at 0, we're in the middle. And if you're looking at the CMB, it's very far back in time. And 2 spots of the CMB have light cones that don't intersect. But if you say I'm going to extend this, I'm going to add a region where I'm going to, the co-moving horizon is, was much bigger, then you can project both back in time, and all of a sudden they do intersect, and they are in causal contact. So how to achieve this, in practice? So as we said, we want to require, the inverse of AH to be shrinking in time. So require the time derivative is to be negative. And you get 2 consequences. A, if you dump that condition in the Einstein equation, you get that the pressure has to be negative, which is quite an exotic type of, you need something exotic to do that. And under the assumption of an almost constant Hubble constant, you get that the scale factor is exponential in time, and hence the big word inflation. Inflation inflates really fast. Now, one way to get negative pressure is you just put a scalar field and just give it some potential, and then you can see that with a large enough potential energy, the pressure can be negative. But now you have to maintain that for a long time, and the canonical way to do that is to have a so-called single fleet slow roll inflation. So you'll have some potential, which is large and has very small steepness, so that the field will slowly roll down. And during this slow down period, you will have negative pressure. And then when you're done, it will go to the bottom, where all the energy will be released. And it's a complicated mechanism, but the end result is that all the energy density of your so-called inflaton will be transferred to other degrees of freedom, like standard model, dark matter, etc. And it's kind of repopulates the universe. So that solves the horizon problem. Now what about the primordial perturbations? Well, what you can do is that, you can write down the action. You can expand, just expand it in perturbation. And if you look at the equations of motion of those perturbations, you find that they satisfy the harmonic oscillator equation. And then you can quantize it and look at the Fourier modes. And then some of those quantities, you just have to extract useful quantities from those. So look at the scalar perturbations of your gravitational field. And you can then ask how different modes of those perturbations are correlated. And what this will tell you is directly how the temperature fluctuations are in your CMB map. So one of the quantities that are important that we'll look at later is the amplitude of scale fluctuations here. You can also look at the tensor part of the perturbations, which will tell you something about gravitational waves. Now, 2 quantities I want to define just for later convenience is the tensor to scalar ratio. So this is basically kind of the ratio of those 2 quantities, the scalar and tensor to scalar perturbations. And since we already measured the scalar perturbations, we know this would be a direct measure to the tensor perturbations. And I also want to define the spectral index, which tells you how the perturbation changes with scale. How the fluctuations are different for different modes. So now, what does observation tell us? Well, the first thing is, we know the universe is very, very, very flat. And in fact, this was a problem in cosmology, that this looked so fine-tuned, because AH, the inverse of AH, which was supposed to, gets bigger and bigger, which means the flatness is an unstable solution. It's like an unstable fixed point. With inflation, you can use it to solve the first two problems, and you get this one for free because it tells you that the flat solution is an attractor because whenever the h is going to go to 0, which force omega a, which is your curvature parameter, to be equal to 1. And then you can ask about Gaussianity. So as I said, the inflation, you got harmonic oscillator, which means your distributions are all Gaussian. So you can ask how non-Gaussian is this, the CMB is. And this is usually measured through 3-point correlations, which would vanish for a Gaussian distribution. And so without going into the details, what those numbers are, these have been measured. These are different ways of measuring 3-point correlations. And they're consistent so far, but the errors are huge. So you can't really tell a lot from them. You can ask how something called adiabaticity, which is how different perturbations of different components are related. So in isocurvature perturbation, you can have a place where you have an overdensity in photons, which is then compensated by an underdensity in matter. The statement of adiabaticity is that no, they all grow together and grow, well, reduce together. And inflation mostly predicts, requires adiabaticity. I don't know if there probably are models that can give you some isocurvature, but so far, this alpha naught is a constraint of isocurvature perturbations, and it's very close to 0 so far. You can ask about scale invariance, which what modes of inflation normally predict is that all modes will have perturbation will be, perturbation are the same for all modes, and so far the value is very close to 1. You can ask about phase coherence. So in inflation, different modes all over the sky are going to leave the horizon at the very same time with the same phase, which means later they will interfere constructively. And this is what can generate you this peak pattern, which we observe in the CMB. So this is how the temperature and the E modes that we observe are correlated. Other models of large scale structure, they fail miserably in that. They just give you different phases that will just wash out each other. So you won't get those peaks. So this is a very robust prediction of inflation. But now I want to talk about one bit of evidence, which there's been a lot of talk about lately, which is B-mode polarizations. So if you have some hot plasma and you have some hot regions and cold regions, then from Thomson scattering, can cause the scattered light to be linearly polarized. Now you can split those polarizations into different patterns. When we look at the sky. So these are not polarizations of light itself. So E and B here, they don't refer to, there's nothing electric or magnetic about any of those. It's just you look at the sky, you see how they, different spots in the sky where the light polarizations are pointing. And you can see different patterns. And it has to do with, with the polarization of the gravity perturbations rather than the photons. And inflation predicts tensor perturbations, which can generate B modes. One where the polarization vectors are kind of spiraling like this, as Chris earlier explained. And you can't get them from scalar perturbation. They only come from tensor perturbation. So this year, the BICEP 2 collaboration released some results. So the upper plot, you can see what E-mode signals look like. So you can see if you look at the hot region, around, you see around it that the polarization are kind of in a circle. In a cold spot, they're kind of pointing inwards. Whereas in a B signal, you see them spiraling inwards. And if you look at their abstract, they say that they measure an R of 0.2. And they exclude R equals 0 to 7 sigma. And it goes down to 6 sigma if they include some foreground emissions. Now, but there are many caveats here. This is not really so good for inflation. It's not really something that people expected, but it's fine. They don't really exclude dust or cyclotron radiation, cyclotron effect to more than 2 sigma, which means that's still possible. But there are, and first people say, okay, these are not a big deal. I mean, we can solve this problem later. But then things just kept getting worse and worse. First of all, in their paper, there seems to be tension with what the Planck collaboration constraints the tensor to scalar ratio. So look at this blue region is what the constraints from Planck are. If you assume that your spectral index, the one that measures scale invariance, is itself constant, it doesn't run. And you can see that 0.2 doesn't really fit. It's excluded by Planck. And the only way to fix that is, or one way to fix that, the easy way, is to make your spectral index run with scale, which is not really what you expect in inflationary models. From what I've heard, it's doable, but it's not typical. But worse still is that some people have raised lots of doubts on how well Bicep 2 dealt with their foreground emissions. In fact, lately there's been a paper that claims that R equals 0 is consistent with their, if you look at the Bicep 2 and the Planck data together. So far, you might as well say that there is no confirmation at all of gravitational waves. What everyone agrees is that you have to stay tuned just for more experiments to find out whether these results are true or not. So to conclude, so inflation can solve the horizon problem and at the same time tell you where the perturbations are coming from. And in my opinion, I think there's strong evidence for inflation, but it's nowhere near conclusive. If we find gravitational waves from inflation, that would be a smoking signal, but we're yet to find whether those things exist or not. Thank you for your attention. Any questions? Yes?
Yes.
Mo, so when you say the foreground emission, do you just mean like how much scattering the dust in our galaxy is doing?
I think it's mostly in our galaxy, yeah.
And it's not well modeled. It seems like we would know from infrared how much dust is.
Yeah, so I think what they used, from what I've heard, is that they used a plot from a talk from a given by the Planck collaboration, which as far as I can tell, it means it's not even peer-reviewed plot. But even that plot, it's not robust yet. We still, we need to wait for more data from Planck and possibly other experiments to model the foregrounds better. But that's as far as I know.
Any more questions? Well, thank you so much for doing all these presentations. I think it was very nice. I really enjoyed it. I think all of you did a very nice job, and I'm really proud of you.